In this lecture we will learn how to solve the complex Navier-Stokes equations within power bound of your PC. As we discussed in first lecture, exact solution of NS equations is too much of accuracy. It captures every minute details of turbulent flow. But an engineer is not interested in such a solution. What he needs is an average solution like this. This is in fact average solution of actual solution, where averaging operation is defined like this. So any variable in a turbulent flow can be represented as sum of mean value plus fluctuating value. To get this averaged values, instead of solving actual NS equations, we can solve something called averaged NS equations. Navier-Stokes equations generated after averaging operation is known as Reynolds Average Navier-Stokes equation. The averaged equations are represented here in index notation form. Here F represents external force acting on fluid. But RANS is not purely in terms of mean values, it will have an extra fluctuating component like this, known as Reynolds stress. There are various turbulent models available, in order to represent Reynolds stress in terms of mean quantities. RANS is not so difficult to solve numerically. Current CFD packages use following numerical methods: FEM, FDM, and FVM. Some commercial packages using these methods are listed here. It is clear that FVM is the most common method of all. So in this lecture we will concentrate only on FVM. So, let's go across it. The fundamental flow equations are derived in FVM, using integral approach. Here instead of considering a differential volume we will consider a finite volume of arbitrary shape. And we will say that, when flow passes through it, rate of increase of quantity inside the volume will be same as flux in minus flux out plus generation of quantity. You can apply this to any quantity. Quantity can be either mass or momentum component. Such a concept will lead to conservative equations in integral form. It will have general form like this, where U represents quantity. So I can apply this general form to mass, so U will be density into velocity. It will lead to conservation of mass equation. Similarly, I can apply it for three components of momentum. We will get three more equations, which are a conservation of momentum equations. So again we have four equations in total, this time in integral form. Now the challenge is to solve these equations throughout the control volume numerically. Here there are surface and volume integrals. We will execute numerical integration of these on small non-overlapping cell volumes of arbitrary shape. Such a cell is shown here. In FVM, volume integrals are approximated as volume of cell multiplied by average value of quantity at centroid of cell. Similarly, surface integrals are approximated as midpoint averaged values. So for this cell we have to do same operation on all four surfaces. Now we can apply same operation throughout the cells, which will generate series of equations in terms of averaged values. We can solve them together with help of some boundary condition. An appropriate mathematical solver will do this task for you. Usually CFD solvers use iterative method to get the solution. The steps we have explained so far are summarized here in step-by-step manner. Before winding up the lecture, we will also see a sample CFD problem. Hope you got a good introduction to world of CFD. Thank you.